All right, before we get into our main content for lecture B, I should emphasize one more thing. I'll re-emphasize it here in a few minutes. We saw that field at the end of lecture A had order 8. It had 8 elements. And I said that there was no subfield of that of order 4. That does not, however, mean that there aren't any fields of order 4. There are. There's just no subfield of order 4 for that field of order 8, which feels a little weird because it's contrary to what happens with groups. Right? You got a group of order 8. If it's cyclic, it's going to have a subfield of 4. Okay? So make sure you pay attention to that kind of subtlety. And I'll re-emphasize it as we look at some theorems here. All right, well, these are the theorems I'm talking about. First ones you could call a classification of finite fields. For each prime p, like p equals 2, for example, and each positive integer n, like 1, 2, 3, 4, 5, 6, etc., there is, up to isomorphism, a unique finite field of order p to the n. Okay. By the way, I keep asking that quiz question about fields of order p squared because we did see a few lectures ago that there was a field of order p squared, but it was not isomorphic to z p squared. Okay? That's a pretty powerful sounding thing. A unique finite field up to isomorphism of order p to the n. Because it's unique, we might as well give it a name. In honor of Galois, we call it GF of p to the n. Galois field of order p to the n. I guess they didn't have to do that, but Galois was pretty far ahead of his time. Galois lived in the early 1800s and essentially discovered group theory and field theory on his own before the abstract theory was even invented. The abstract theory that we've been doing in this class was not invented or discovered until the late 1800s, and Galois lived in the early 1800s. So he was doing work that was way ahead of his time, so it makes good sense to honor him. Also, he died when he was really young. He died in a duel, actually. He was like 22 years old or something. I think it was over politics, but some say it was over a woman. But I don't know. It was early French Revolutionary kinds of times, I think. There are lots of political arguments, as there are still today. What kind of structure do finite fields have? We could say more here. As a group under addition, the Galois group of order p to the n, the unique field of order p to the n, where p is a prime and n is a positive integer, is isomorphic to an external direct product of n copies of zp. We saw that in the example from lecture A. Our field was order 8, 2 cubed. We saw that every non-zero element had additive order 2. We saw all the zeros along the diagonal of the addition table, which is a Cayley table. It was isomorphic then to the external direct product of Z2 with itself 3 times. 3 copies of Z2, I should say. That's as a group under addition, ignoring the multiplication. As a group under multiplication, U of G of F of P to the n, meaning the group of units, which would be all the non-zero elements, because it's a field, is cyclic of order p to the n minus 1. It's isomorphic to z sub p to the n minus 1. So in the example we did, field of order 8, there were 7 units. They formed a group of order 7. It was cyclic z7. 7 is prime, but in general, p to the n minus 1 doesn't have to be prime. Right? And 2 to the 4th, 16 minus 1, 15 is not prime. But this group is still cyclic. Textbook doesn't bother using the U notation here, it just says the group of non-zero elements is cyclic. Okay? But you certainly can use the unit notation if you like. So if it's cyclic, it's going to have a generator. Is the generator x? Beta in that example? Beta was a generator, x was a generator in that example, but that's not necessarily true in general. So you've got to be careful. A corollary of really the first part of this is as a vector space over ZP, the Galois field of order p to the n has dimension n. That makes sense? Take this example again. I'm thinking about the additive group here, which is isomorphic to this, so just go ahead and think about this. This is a vector space over Z2. If we only focus on addition and multiplication by scalars, where the scalars are from Z2, which is a field, 0 or 1. We can multiply by the scalar 1, for example. Turns out to have dimension n, it says here, which in this case would be dimension 3. The exponent there. So what's a basis? A basis, if you were thinking of it this way at least, would consist of these three. Really, these things are coordinate vectors. If we were thinking of it in terms of the original notation, it's not clear offhand what would be a basis. Okay, but if we were thinking about coordinate vectors, this would be a basis. Okay, I know it's a little confusing. Not sure we're going to have time to come back to that, but it's going to have dimension n in general, and in this case it's going to be dimension 3. Using this notation with the square brackets that I showed you last time, which looks kind of similar to index notation from group theory, but it is different, you can write this. You don't say index here in field theory. You say degree. The degree of the Galois field of order p to the n over the Galois field of order p, which, by the way, is isomorphic to ZP, is n. This is emphasizing that this Galois field of order p to the n has dimension n as a vector space over the base field, the smallest subfield. Okay, so you're going to have a basis of n elements. Actually, we can write down a basis in the example that we did. By another theorem that we've looked at before. So coming back to that example, that was our original polynomial that was irreducible over Z2. And in the field extension E, we took beta to be a 0 of this polynomial. If you want to be technical about it, you could think of beta as being x plus the ideal. If you want to be extra technical about exactly what beta is, you could think of beta as an abstract symbol satisfying field properties based on what we talked about. In E, beta is a 0. And this was irreducible over Z2. We had a theorem back in chapter 20, which I have talked about. I've talked about this one before. Theorem 20.3. E really is the same thing as Z2 adjoined with beta. And that is isomorphic by theorem 20.3 to Z2x mod the ideal generated by f of x. Trying to remember theorem 20.3, it's on page 343. And that theorem also emphasizes that a basis of this field extension as a vector space over the base field is going to consist of 1, the 0, and then powers of the 0 up into a power 1 less than the degree of this irreducible polynomial. So 1 beta and beta squared is a basis for E over Z2. Back over here, we were thinking about it in terms of its isomorphism class when I said that was a basis. That's isomorphism class kind of thinking. This is coming back to the original example and saying this is a basis. And you can write each element then as a unique linear combination of those, which only makes sense because of it's a polynomial that's quadratic. A beta squared plus B beta plus C, where A, B, and C are in Z2. But theorem 20.3 also emphasized you could write each element in a unique way like that, which is what emphasizes that this is a basis. Which is also emphasizing this. We're looking at the Galois field of order 8, p to the third. We're looking at this example. Over Z2, the dimension here is 3. I still wanted to talk about coordinate vectors, but I think I still want to skip it at the same time. Get on to some other things for the sake of time. Look at this back here. You got to think carefully about this one. It's easy to get confused. For each divisor m of n, the Galois field of order p to the n has a unique subfield of order p to the m. Moreover, these are the only subfields of the Galois field of order p. First thing I want to say about this is this does not contradict the fact that our field of order 8, our example, did not have a subfield of order 4, even though 4 divides 8. The reason is the power of 2 squared, which is 2, does not divide the power of 2 cubed, which is 3. There is a field of order 4, but no such field can be a subfield of the field of order 8, even though 4 divides 8. According to this theorem, the reason is because the power 2 does not divide the power 3. Two is not a divisor of 3. Because those are the only subfields of a Galois field of order 2 cubed, for example, is going to be when the power divides 3. There is no subfield of order 4 in a field of order 8. There would be a subfield of order 2, p to the 2 to the first power. 0 and 1 would be a subfield of order 2, but no subfield of order 4. So finite fields can be essentially completely classified and understood in an abstract setting, at least. With particular examples, you have to still work out the arithmetic, so to speak. But in the abstract, they are essentially completely understood. All right, with our remaining time, let's go back to chapter 21 now. We've been spending most of our time in chapter 22, mixed with chapter 20 today. Let's go back to chapter 21, which is going to be what your completion assignment to work on is going to be from. Again, probably finishing this by Monday is too difficult. Do your best to finish it for sure by next Wednesday. Maybe even shoot for next Tuesday. The homework from chapter 21 I'm talking about. Quick review of types of field extensions. An element in some field extension that is a zero of some non-zero polynomial in the base field, coefficients in the base field, is said to be algebraic, again, when it is a zero of some polynomial. Like, for example, I is algebraic over q, for example, because it's a zero of x squared plus 1. Square root of 2 is algebraic over q as well, because it's a root of x squared minus 2. Numbers that are not algebraic are called transcendental. Pi is an example of a transcendental number. E is also an example of a transcendental number, though those are difficult things to prove. It's difficult to prove those are not algebraic. It took a long time. As our author says, you may have noticed pi plus e, at least to the point where this book had been published, was not known to be transcendental or not. It could theoretically be algebraic because nobody's yet proved it was transcendental. You would think it would be, but nobody's proved it yet. Kind of strange. Okay. An extension is algebraic if all the elements in the extension are algebraic over the base field. And if there's at least one element that's not algebraic, you call it a transcendental extension. So if there's one element that's not algebraic, there's going to be more. Extensions of this form where you adjoin one thing are called simple because you just have one thing. Again, there's this historical curiosity which is actually important as well as far as the history behind algebraic versus transcendental numbers and the fact that the existence of pi being transcendental proved you cannot square a circle. I wanted to send you a video about that. I think I'll try to send you a video about the fact that you can't square a circle. Which sounds really weird. What does it mean to square a circle? Well, the video would explain. That's a historically important problem that goes back a couple thousand years to the Greeks. Think about straight edges and compasses. It's related to that. Let's get on to the foundational theorems, though. In chapter 21. First of all, again, as you look at this, it is good to use your imagination to remind yourself that F is the base field and E is some extension, which the notation is convenient, E for extension, F for field. They're both fields, though. A is in E, which does mean it could be an F. A could be an F. This theorem is still true when A is an F. But most commonly we imagine A to be an E, but not F. And in fact, if A is transcendental, it can't be an E. Excuse me, it can't be an F. Because if A were an F, it's going to be a zero of x minus A. It'll be algebraic. Anything in F is algebraic over F, because it's a zero of x minus A, which would be in this polynomial ring if A is in the field. But transcendental things then have to be outside of F. And it turns out that if you adjoin this thing, which again, remind yourself what this notation means, this is the smallest subfield of E that contains both F and A. It's probably the most efficient way to say it. that turns out to be isomorphic to this thing, which again, this is not a function. This is the field of rational functions. This thing is not a function, it's a set. It's a set of rational functions, right? Field of fractions or field of quotients, you might say, or polynomials. So that means you can represent elements of this as rational functions of A, really, where x gets replaced by the element A, like I, for example. If, on the other hand, A is algebraic over F, then this is true. This isomorphism we've seen a lot. This field extension is isomorphic to this factor ring, which is a field as well. This is going to be this will be a maximal ideal in there. And P of x is going to be a polynomial minimum degree. That makes this true. And P of x will be irreducible over F. If A happens to be in F, then P of x will be linear. It'll be something times x minus A. If A is not in F, then P of x would have to be at least quadratic. Keep those kinds of thoughts in mind as you read these things. Turns out there is something called the minimal polynomial for A over F. You can take the P of x to be monic, leading coefficient of 1, sort of like the simplest kind of irreducible polynomial, of which A is a 0 and 4. This is the theorem. In fact, as far as the completion assignment goes, first problem is to prove this theorem and this theorem, actually. It's not as hard as it might look. You just mimic what the book does to some degree in the proof of this one. Wouldn't be easy if you didn't have that to mimic, but if you mimic it to some extent and make modifications, you can prove these things. So there is a polynomial that's irreducible in f of x and monic as well, for which A is a root. And moreover, if you have such a polynomial, and you've got some other polynomial, f of x, for which A is a 0, then in fact the minimal polynomial divides f of x. Okay? These can be useful things. It's sort of easiest to think about these things with the minimal polynomial. Here's a foundational definition and a couple more foundational theorems. I showed you these before as well, but go over them again. Let E be an extension field of F. We say E has degree n over F, and write this notation that we talked about a few minutes ago. If E has dimension n as a vector space over F. So again, this is similar to index notation with groups. Right? Index notation with groups looked like this. That was the index of H and G. It represented the number of distinct left cosets excuse me, of H as a subgroup of G. This notation is a little different, though. We've got square brackets instead of absolute value signs. And these things are fields, not groups. Though, of course, fields are groups, but we're not thinking about the number of left cosets. We're thinking about this as representing the dimension of E as a vector space over N. Any field can be thought of as a vector space over some subfield. I did mention that. It's really important to realize that. If this degree happens to be finite, then we say E is a finite extension of F, otherwise we say it's an infinite extension. Theorem, finite extensions are algebraic extensions. If you've got a finite degree extension, it's got to be algebraic, not transcendental. The converse of this theorem is not true. Algebraic extensions actually can be infinite extensions. And the book gives an easy example to think about. If you keep adjoining roots of 2, square roots, cube roots, fourth roots, fifth roots, etc., technically you can define such a thing, and it is an extension of Q. And it is algebraic, but it's not finite. The degree of this as a vector space over Q is going to be infinite, at an infinite dimensional vector space. No finite basis. Which seems reasonable looking at it. So finite implies algebraic, but algebraic does not imply finite. And then we have this fact. Let K be a finite extension of E, and E be a finite extension of F, then K is also a finite extension of F. You can make a blob picture. K is even bigger. You'll also see these tower pictures like this. E is an extension field of F, K is an extension field of E, therefore K is also an extension field of F. If this is finite degree, say the degree is m, and this is finite degree, say the degree is n, then overall K is a finite extension of F, and the degree of K over F is m times n. And it's actually a pretty cool thing, the proof, and how you can actually even apply the proof. Turns out if you look at page 357 and look through the proof, what they do to prove it is they take a basis for E over F and a basis for K over E, and they obtain a basis for K over F by multiplying the elements in the bases. Look at the proof. They multiply the x's and the y's in that proof that are bases for E over F and K over E to get a basis for K over F. And that's essentially why you multiply the degrees. And they even apply that in an example, which you should definitely study. Some good examples to study here are on pages 358 and 359. Examples 3 and 4 really illustrate these facts here, and also 3 illustrates the proof of this last fact that I just mentioned. Definitely give those a good studying. Pretty foundational. And it's going to help us understand Galois theory next week. Okay. So the motivation here, the overall big picture of what we're heading for is Galois theory. We want to understand the historical importance of Galois theory. What is Galois theory all about? And some basic examples. Knowing this theorem is going to be important for Galois theory. And in fact, what you're going to see is maybe it's not a coincidence that this notation is similar to index notation for groups. There is actually a relationship between them. What we're going to see with Galois theory. Okay. That's what's coming next week. See you then.